So the first big problem in calculus came from how do we find an instantaneous rate of change, which turns out to just be a slope at a single given point. Well, we found out that that's just a derivative, and we developed the limit definition of derivative, and then from that we were able to develop easier rules to use to find derivatives, right? And we found all these different applications of derivatives. We can optimize functions, we can solve related rates problems. The other half of calculus comes from talking about accumulation of change, namely this thing called the area problem. And the area problem is exactly what we just defined, which was, hey, we have this random curve. I want to find the area of that region S underneath it. I don't just have a geometric formula for that, so what do? And so Newton and Leibniz, the two fathers of calculus, figured it out. Here, sorry, go ahead. No. We'll spend less time on integral calculus. So here's what they did. Pretty ingenious. They go, okay, first thing we're going to do is subdivide the region into equal subintervals, okay? So what I mean by that is I'm going to go on the x-axis, and I'm just going to divide this up. In this case, I'm going to use 4 intervals. So you can see I have these 4 intervals. 1, 2, 3, 4. Our overall interval is the interval from 0 to 1, but each one of these is called a subinterval. And we're going to get kind of precise in some of our notation here, so make sure that you notate really well. We're also going to jump into some sigma notation. Sigma and calculus notation are basically the highest math that they'll ever throw in a movie to try and make it look like somebody is smart or doing high-level math. And it's always floating around their head. Yeah, well, that's just like geometry formulas for the most part. There might be a sigma tossed in there. All right. And then what we're going to do is, in this case, we're going to use right endpoints. So I'm going to notate what we're doing. We're going to call it R sub 4. And what it means is right endpoints, and the little subscript is just how many subintervals I've divided it up into. So 4 subintervals. Say again? R is going to indicate what we're using to get the height of our rectangle. So here's what R means. On each subinterval, I'm going to go to the right-hand endpoint. So first subinterval, this would be the right endpoint, right? And then I'm going to trace up until I hit the curve. Boom. That's going to be the height of my rectangle on that subinterval. So now I'm going to create a rectangle. Boom. Second subinterval, go to the right endpoint, trace up until you hit the curve. That's the height of that rectangle on that subinterval. Continue on. Right endpoint, that's your height. Right endpoint, that's your height. Okay. Now, we generally call the width of the subintervals delta x. That's what it is. It's a change on the x-axis, right? And when we create our own subintervals like this, it just makes sense to keep the width of the rectangles consistent across your entire interval. So basically what I can say is that for each one of those rectangles, its Its base is delta x. Does that make sense? What would the actual value of delta x be in this case? No, what's the actual value? How long is the whole interval? 1. So it's, you take the length of the interval and you divide by how many subintervals you have, right? So it's 1/4 in this case. And so that's a formula I'm going to give you. Delta x equals b minus a over n. We generally think of the leftmost endpoint to be point A, the rightmost endpoint to be point B. N is just the number of subintervals. Great. So for each of these rectangles, they have a width of 1/4. Now the height of the rectangles will depend on the function. And what I want to do is label these indices. Indices are the values of the endpoints. So the way we label indices is your leftmost endpoint is x sub 0. And then it would be x1, x2, x3, and then your rightmost endpoint in this case is x4. Meaning your index label should always match, like the last one should match how many subintervals you have. So I have 4 subintervals. My last index label is x4. Okay? And you can always ensure that by starting the leftmost is x0 equals 1. You're exactly right. B equals x4 equals 1. A equals x0 equals 0 in this case. All right, well, I should be able to figure out the values of x1, x2, and x3. They're just x coordinates, right? And here's how we do it. Any general xi will be equal to your left endpoint plus I times delta x. Remember, delta x is the width of the gap. So for example, let's say I want to know what x1 is. I'll take my a, which is 0 in this case. I'll add 1 times delta x, which is 1/4 for us. So x1 is 1/4. That's just the actual value of the x coordinate there, right? Well, what's x2? You can probably think of this without having to use the formula. If this is 0 and then 1/4, then we add another 1/4 to that. x2 is 1/2, right? But I can just verify for you that the formula works. So x2 equals 0 plus 2 times 1/4. That's 1/2, right? All right. So now I can label actually all my index values. So what we have is 1/4, 1/2. What's x3 going to be? 3/4, and then 1, right? All right, so now we can actually start finding the areas of these rectangles. So all I'm doing is I'm going to use the area of these rectangles to estimate the area under the curve. It's just a jumping off point. It's an estimate. Maybe it's not a great one, but it's a starting point. So each rectangle is base times height. So the base of the first rectangle is 1/4. Now I can get the height of that rectangle based off the function, right? The height is just going to be the y value here. How do I get the y value at that point? What is that function? What is this? What's the equation of that curve? That's y equals x squared, right? So to get the y value, which is what I want this, I plug in the x value and square it, right? So what's the height of this first rectangle? That's 1/4. What happens when you square it? 1/16, right? 1/4 squared is 1/16. So that first rectangle, base is 1/4, height is 1/16. There we go. I've covered this area. Second rectangle, what's the base? This base? Still 1/4. They're all 1/4 for the base. What's the height? The height, I'm now plugging in this x value, right? And squaring it. So what's the height going to be? 1/2 squared is 1/4 plus. Now I've done that rectangle. Third rectangle, what's the length of the base? Plus 1/4 times, what's this height? Square 3/4, right? So 9/16. 9/16 plus, last one, 1/4 times 1 squared is just 1, right? Is this estimate, is it going to be an overestimate or an underestimate of the true area? Over, because of this, right? There's that overlap, correct? All right, but it's a starting point. So pop that into your calculator. One thing I'll show you, every one of these terms has a 1/4 in it, meaning I could factor out the 1/4 and then just add the y values together. So 1/16 plus 1/4 plus 9/16 plus 1, sorry. All right, so if we do that in our calculator, we get 0.46875, yeah? And we all agree that that would be an overestimate. Great. Well, that's a starting point. How could I make it better? That's an estimate. How could I get a better estimate? So R4 is, what was it? 0.46875. Yeah, if we could, right? But then to be able to do that, they're not really triangles because they fall along a curve. But it's pretty similar to the idea that we had when we were trying to get an instantaneous slope, right? We started with 2 points on the curve, and then we just moved 1 point closer and closer to the fixed point. And it's kind of a similar idea here. All I'm going to do is use more subdivisions. So what if I wanted to do, instead of R4, what if I divide it in half, divide it in half, and divide it in half again? Is that 8? 1, 2, 3, 4, 5, 6. One more. 7, 8. Okay. So what if I use 8 subdivisions instead of 4 and I actually calculate R8? I'll show you how to do this a little bit more efficiently in your calculator. All right, so now I use 8 subdivisions. I'm going to use the right endpoint to get the height of each rectangle. Easy way to do that is start from the right side to make your rectangles. All right, so we can already visually see still going to be an overestimate because we still have these overlapping areas, right? But do you think it's going to be a better or a worse estimate? Just based on visuals alone. Probably better. Let's see if it's any different. All right, help me out with a few things here. What's delta x going to equal in this case? 1 over what? Good. 1 over 8. The width of each rectangle is 1 over 8. And since rectangles have the formula for area of base times height, I can just factor out that base, right? In fact, I'm just going to put it here at the end, 1 over 8. And then all I have to do is add up the heights of all those rectangles. And the heights of all those rectangles is just the x-coordinate squared, right? And so my first height comes from that x-coordinate. What would this x-coordinate be? Just the x-coordinate. That's 1/8, right? And so it's just going to be 1/8 squared plus, that would be the height, right? That's the way I get the height, is just squaring the x-coordinate. What's the next x-coordinate? 2/8. Then 3/8, 4/8, 5/8, 6/8, 7/8, 8/8, yeah? So that's all I'm going to do. So plus 2/8 squared plus 3/8 squared and so on up to 8 out of 8 squared. Yes, I know that 8 out of 8 is 1. But your calculator can handle the simplifying. I don't need to do that right now in my head. So let's do a little trick in our calculators. If you have one with you, get it out and practice this with me, okay? The only way you get fluent with your calculator is by following along, actually doing the motions. So we're going to use actually a statistical function. I'm going to go stat, edit. It should pull up these lists. If there's any stuff in your lists, right? So if you have some random data in a list like this, go up, highlight the list name and hit clear, and then scroll down.
Mr. Toller, we can't see the calculator.
Oh, sorry. Thanks, Olivia. So I went to stat, edit.
That was Naomi, but thank you.
Oh, thanks, Naomi. Sorry. All right. Here's what I'm going to put in list 1. I'm going to put all those heights. Actually, not even the heights. I'm just going to put the indices in this case. So I could do 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. So those are just my indices, right? So to actually turn those into heights, I want to square all those, right? So we're going to do a light computer programming here. Highlight list 2 so that it actually says L2 equals down here. So actually highlight the name of L2, not the first cell, the name L2. And I'm going to tell L2 equals L1. There's a shortcut if you hit second and then 1. And then I'm going to square it. So L2 equals L1 squared. Boom. So now it's taken all the data in list 1, which were our indices, and it's squared them. So now it's actually populated. Those are the heights of each of my individual rectangles, right? Those are each rectangle's height. It's this, yeah? You guys follow so far? So far, so good? All right, now let's go to the main menu. So second mode, that quits to the main menu. And I'm going to do 1/8 times. So that's the width that I factored out. And now I want to tell it to add up list 2 for me. Okay? You guys see above stat, it says list. That's where we can act. Oh, sorry, guys. Sorry, online. I did it again. So I did 1/8 times, and then you see above stat, it says list. So I'll hit second stat. This is where you can access all information about lists. I'm going to scroll over to math. I'm going to choose the 5th option. Sum list 2. .398. So that 1/8 sum list 2, it just tells my calculator to do exactly what I have written here. I did 1/8 times the sum of what I had in list 2, which is all those heights, and I get .398, which is a better estimate. All right, it's still an overestimate. You can see I shaded in all those red overlaps, but it's a better estimate than our 4 was. What do you think is a better estimate than our 8? Hey, if we want to get exact, how many subintervals are we going to have to use? Infinitely many. But the more subintervals we use, the better the estimate of the area we'll get. Does that make sense? That's the general idea. Now, this is a cumbersome process, but as we just saw in our calculator, it's pretty easily programmable, right? All right. Before I go back, let's do one more. I want to talk about, I specifically used R4 and R8, but we could have gotten the heights of our rectangles using different points on our subintervals. So let's, if I re-subdivide this into just 4, let's say I wanted to use left endpoints instead. So I wanted to do L4. Well, L4 means that I'm going to look at a subinterval. So let's just look at this one. I'm going to use the left endpoint on that subinterval to determine the height of the rectangle for that subinterval. Does that make sense? So here's my subinterval. This is the left endpoint. Go up until I hit the curve. That's the height of that rectangle. Does that make sense? Now I'm using left endpoint. So the height of this one would be here. The height of this one would be here. What's the height of this one? It's 0. It's a degenerate rectangle. It has a height of 0. Our left endpoint's going to provide me with an overestimate or an underestimate. Under, right? There's all this. So that's the area we're going to get, but we're going to be left with all this negative space that we're not accounting for, right? So let's just real quick write out what L4 would be. Our delta x, our width, would still just be 1/4 in this case, right? And we would still find our heights by plugging them into y equals x squared. But in this case, we would use the endpoints on the left side. So I'd have 0, I'd have 1/4, 2/4, and then my last one would be 3/4. That's 0 squared plus 1/4 squared plus 2/4 squared plus 3/4 squared. All right, so that gets me 0.219. Compare that to R4, so that's L4, and R4 is 0.46875. So one's an underestimate, the other is an overestimate, right? So the real answer is somewhere between them. And as you increase the number of subintervals, you get better and better estimates, right? All right, so now let me reveal. Here we go. Here's when we're increasing the number of subintervals. So I've done it for 10, 20, 30, 50, 100, and 1,000 subintervals. And you can see the various left endpoint estimates and right endpoint estimates. And the right are always over, the left are always under, but you can see they both seem to approach what? If you have to make a guess, if I base your entire grade on it, what does it look like those areas are approaching? 0.3 repeating, which is 1/3. I think that's a decent guess. All right, and this just shows you kind of the visual. You can definitely visually see as we use more subintervals, we get better and better approximations of the area underneath that curve, right? And as Ajay pointed out, if we want an exact area, how many subintervals are we going to need to use? And luckily, we have the tools to be able to do that. We know how to take limits at infinity. So what we want to do is let the number of subintervals n approach infinity. And our guess, just from looking at the pattern, is that it would be 1/3, right? I think that's a pretty good guess. Okay, couple formulas I already gave you. Delta x is b minus a over n. Sorry. Which one? This was the formula. This one? Okay. So even though one starts as an overestimate and the other starts as an underestimate, as long as we let the number of subintervals approach infinity, they'll both approach the true area, okay? These are formulas I already gave you. Okay. So the area of a region S that lies under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. So each one of these is an approximating rectangle, right? So we have base times height. The height is given by the y value of the function at that index. So you do that for every subinterval. You do base times height, base times height, base times height. And if we let the number of rectangles approach infinity, we get exact area. And it doesn't matter if you use right endpoints to get the height of your rectangles, or if you use left endpoints to get the height of your rectangles. And in fact, it doesn't matter if you use any point on the subinterval to get the height of the rectangle. Meaning, it doesn't have to be right or left endpoints. We could have chosen the midpoint on the subinterval, drawn a vertical line until we hit the graph, and use that as the height, right? So take a look at this. This is the true formula. This is like the most general formula. And this little asterisk just means that xi could be any point on the subinterval. Meaning, like, if I look at x2 star, that's the subinterval between x1 and x2. they used the middle, drew a vertical line until we hit the graph, and used that as the height of our rectangle. That's fine. As long as you let the number of rectangles approach infinity, it doesn't matter what point on the subinterval you chose to get the height of your rectangles. You'll still get exact area as long as you use infinitely many rectangles. Does that make sense? So that's all that little star means, is that x1 star could be any point coming from this first subinterval. So we're not going to do too much more. I have a couple more examples, but today I just want you to wrap your head around this idea, like the general algorithm we're using to find areas under curves. We start with rectangles. The more rectangles we use, the better estimate we get. We want exact area, use infinitely many rectangles. We'll get to the actual math of that in a couple sections. Dylan?
Did you find like the average is overestimate and underestimate?
Yeah, and we are going to. That's actually called the trapezoidal rule. So when you do that, what you're actually making, that's a great question. What you actually make in that case is a trapezoid. And so, for example, what it ends up being is it connects these endpoints like this. And so this is a trapezoid. It's kind of a trapezoid that you're not used to looking at. It's like tipped over onto its side. But that's called the trapezoidal rule. And that's actually your best. If all you're trying to do is estimate, you're not trying to find exact area, then the trapezoidal rule will produce the best estimates for any number of subintervals. But we will get there. All right, let's talk about sigma notation. Have you guys seen this before? This guy is called a capital sigma. Okay, well, I'll reteach it real quick. All it means is add up. Sigma just means add. And it's just a shorthand notation for when we have to write a sum that has some pattern and we don't want to write it out longhand as a big sum. You saw once you start doing many subintervals like R8, it kind of becomes a pain to write out all the terms. And so we call this guy that is below the sigma, this is your iterating variable. Iterating just meaning like counting. And the general rule is your iterating variable will iterate by the whole numbers. So it'll go 1, or whatever you have it starting at, then it'll go up by 1. So 1, 2, 3. The n is your stop. That tells you when to stop. So I'll give you a couple of straightforward examples. Let's say I wanted to add numbers 1 to 4. I could write that like this. Sigma from I equals 1 to 4 of I. Whatever's in front of the sigma is the formula that you're going to apply to I. So you apply it. So I start here. I start with 1, plug it in for I get 1. Once you've applied your formula, you iterate, and you always add between iterations. So sigma means add. So 1 plus, what comes after 1? Not everybody at once. What comes after 1? 2. So then I would apply my formula. In this case, my formula is just I itself. 2, then iterate. After 2 is 3. Iterate. After 3 is 4. And I know to stop at 4 because that's my stop on top of sigma. So 1 plus 2 plus 3 plus 4 is 10. There you go. Let's say I wanted to add the first 5 even numbers. Can I create a formula to do that? Sure. Sigma I equals 1 to 5. And then how do I guarantee what's the formula to create an even number? Plus 2 times 2. So it would just be 2i, right? So when I plug in I equals 1, what's the first term? 2. Iterate, plug in I equals 2, what's the second term? Plus 4, plug in I equals 3, we were going to get 2 times 3, which is 6, plus 8, and then plug in 5, we get 10, and then we would stop. Does that make sense? So let's look down here. The sigma notations for the right hand and left hand sums are given to us. We're given I equals 1 to n, f of xi delta x. So if I wanted to write this in an expanded form, first thing I would do is plug in 1 for I. So the first term I would get is f of x1 delta x, right? And then I would iterate, plus, plug in 2, f of x2 delta x. And then we would continue on, and we would stop at n, right? So my last term would be f of x n delta x. All right, how is that different than the one below it? We're still starting at I equals 1, but then look at the formula. It's slightly different. So what's my first term going to be here if I write this in expanded form? It's going to be f of x what? 0. If you remember, x0 is your left-handmost endpoint, right? So f of x0 delta x, and it's going to end at f of x n minus 1 delta x, right? So basically, this is the left endpoints, and this is the right endpoints. Because the first one goes from x1 to xn, and the bottom one goes from x0 to xn minus 1. All right. Write this formula down. I think you'll need it maybe for part of your homework. I don't even think it's this one. But this is just an expansion formula for the first n perfect squares. Meaning if what I'm trying to do is add up 1 squared plus 2 squared plus 3 squared, and so on up to some number n, that's a formula for it. There's another one I'll give you, which is just the sum of the first n numbers. Which was famously, so this mathematician, Carl Friedrich Gauss, one of the most prolific in history, super precocious kid, very annoying, right? Annoyed his math teacher to no end, because he's much smarter than his math teacher. But there's this story about him as a 6-year-old, like completing his arithmetic work too quickly. And so his teacher was getting annoyed and goes, go add up the first 100 numbers, 1 to 100. Come back when you have the answer. Just to try and get him off of her back. And he came back 2 minutes later and said the answer is 5,050. And the way he did it was this. So let's look at that formula. If I want to add just the first n whole numbers, that would just be sigma I from I equals 1 to n, right? Because that would be 1 plus 2 plus 3 and so on up to n. Everybody agree with that? Feel mildly comfortable with the sigma notation? All right, well, that adds up to something. Let's say that it's S for sum. And just to illustrate something, I'm going to go plus the second to last number would be n minus 1, right? And then plus n. Everybody okay so far? All right. Do you agree that that sum would be the same if I reverse the order? So if I do n plus n minus 1 plus n minus 2 and keep going until I get down to plus 2 plus 1, should give me the same sum, yeah? All right, well, there's a property of equations. If you have two true equations, you're allowed to add them, and they'll still be, it'll give you a true equation again, okay? So if I add these together, on the left-hand side, what do I have? Let's go. You all passed algebra. What should I call S plus S? 2S. Now on the right-hand side, let's look at this. These kind of pair up, don't they? So I have n plus 1. I'm just going to put it in parentheses. And then I have n minus 1 plus 2. What does that simplify to? N minus 1 plus 2. Still n plus 1. And then I have n minus 2 plus 3. What does that simplify to? Still n plus 1. Guess what? Every one of these is going to pair off to be n plus 1. Do we see that? All right, how many pairs of n plus 1 will we have? If I'm adding up 100 numbers, I would have 100, right? If I'm adding up n numbers, I would have n. Well, we have something that can help us simplify repeated addition, and that's multiplication. So doesn't that just equal n times n plus 1? And then what I want to know is the sum, so I can just divide out the 2. S equals n times n plus 1 divided by 2. All right, so if you want to know the sum of the first 100 terms, that's just 100 times 101 divided by 2. That reduces to 50. 50 times 101 is 50/50. All right. So we will use that, but here is the one. That's a similar formula for finding the sum of the first n squared terms. All right, last thing we'll do is translate this to the distance problem. So if we want to find the distance traveled by an object during a certain time period, if the velocity of the object is known at all times, well, distance is just equal to velocity times time. But a lot of times, velocity can vary, right? Specifically, let's talk about a falling object. If you let an object free fall, its velocity is increasing, right? But it's increasing in a way that we know. It's increasing due to acceleration, right? All right. Suppose that the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval, and we take speedometer readings every 5 seconds and record them in the following table. Seems extremely inefficient. All right, but here we're given time in seconds and velocity in miles per hour. Well, the first thing I did for you is I went ahead and converted to feet per second so that our time and our velocity kind of had matching units. Time is now in seconds. Velocity is now in feet per second instead of miles per hour. Does that make sense? And I want to find the distance that I traveled over that interval. Well, I'll tell you, the distance is just going to correspond to the area under this graph. And an easy way to think about it is just think about the units. Area generally comes from multiplication, right? Well, if I have time in seconds and I have velocity in feet per second, what happens when you multiply feet per second times seconds? What are you left with? Feet. Seconds cancel, and we're left with feet. Feet is a measure of distance, right? So the distance traveled is going to correspond to the area under the velocity graph over the time interval that we're interested in looking at, okay? But we're not actually given a function, we're given a bunch of points. So we're just going to estimate this just like we've been doing so far. I'm going to show you how to create a scatter plot in your calculator. So get out a calculator. Does anybody here not have a calculator with them? Here, come borrow mine, Maisie. So I want you to practice doing this. All right. We're going to go back to the list menu. So stat edit. We're going to clear out these lists. So highlight the list name and hit clear. Scroll down. Highlight the list name and hit clear. Scroll down. In list 1, I want you to put your times. The times are just from 0 to 30 counting by 5. So 0, 5, 10, 15, 20, 25, 30. Good. So list 2 is going to be our velocities in feet per second. So I'll give you those again. 25 times 5, it's 31. 35. 43. 47. 45. And finally 41. All right. Before we graph this as a scatter plot, let's go just to y equals. If there's anything there, clear it out. I just don't want a bunch of other graphs graphing over our scatter plot. All right, so your scatter plot you can find in stat plot, which is second y equals. Just hit enter on plot 1. I'm going to turn it on, so you need to hit enter so that it highlights on. The type, you want to make sure it's highlighted the scatter plot, which mine already is. Our X list is where we keep our X data, which for me was list 1, and your Y list should be list 2, unless you put it somewhere else. But there are shortcuts to your list names on the keypad. And then your mark, this is where you really get to be creative and express yourself. You can choose between a hollow box, a plus sign, a dot, or Chase, wait for it, a smaller dot. All right. So now we're going to quit out of there. Everything's turned on. We're going to go to zoom. The 9th option, zoom stat. And this will fit the window so that it shows all your data. So 9th option. Boom. There we go. All right. So let's use, I'm going to decide arbitrarily, meaning no reason I'm doing this instead of left endpoints, but I want to use right endpoints. So we're going to use right endpoints, and I'll annotate on this. If I just draw a vertical line straight down from my points, that's going to divide my interval up into a certain number of subintervals. These are supposed to be straight. Bear with me. All right, how many subintervals do I have? 1, 2, 3, 4, 5, 6. So what I'm finding right now, I'm going to estimate that distance traveled using R6. And I said we're going to use right endpoints, so I'm going to start at the rightmost endpoint. There's my width. Oh no. All right. This one. Awesome. Now, if you go back to stat edit, you should be able to tell me what delta x is, because I think it's the same for all of these. How wide is our time interval? 5 seconds, right? Meaning each one of these rectangles has a base of 5. Does that make sense? All right, so I'm just writing that down. And now I just need to find the height of each rectangle, which I can do. I'll hit trace. Is that the height of my first rectangle? Is that the height of my first rectangle? No, that's the left endpoint, and I decided I was using right endpoints. Is that the height of my first rectangle? Which is what value? 31 plus 35 plus 43 plus 47 plus 45, and finally 41. Each of those is a velocity given in feet per second. And we're multiplying that sum by 5, which is given in seconds, right? So it's going to leave us with an answer in feet, which is the total distance we traveled over that 30 seconds. Does that make sense? All right, so here's what I wrote out. Can you guys add that up and multiply it for me? I don't have a calculator in front of me anymore. What was it? 900? 985? Any disagreement? Uh-oh. 1210? 1337? Oh boy. Um, $13.35, but that's if we use the first y value, which we shouldn't be using because we're using right endpoints. So if I delete that and then redo that, 1210. Okay. I agree. So it's 1210. What are my units again? Careful, we're taking feet per second and we're multiplying it by seconds. So it's just going to leave us in units of feet, right? Which is a distance, which is what we want. All right, folks.